Thank you for the introduction. My name is Francesco Gliotti. I'm a building engineer from Politecnico di Torino. I'm working in the field of drawing and digitalization. So, as you can see by the title, my research introduces BIM, Building Information Modeling, in order to enrich the survey in the process of investigation of building. My research promotes the use of parametric structural model to organize the knowledge of existing building. The approach explores the potential of building information modeling intended both as building information model, so a three-dimensional representation of the building based on object with information, so a database of information. And the other meaning of BIM, that is building information modeling, so a working method that allows a work sharing of information. Specifically, the core of my research is focusing on maximizing BIM data for structural survey design activities. Tests have been performed on a pavilion school complex of the 70s located in Turin. The building is spread over 3 floors above the ground, and the structure is made of reinforced concrete. This case study is part of the BIM project that is aimed to define a replicable method for the digitalization and the management of the public heritage, in this case of the city of Turin. So, the investigative methodology aims to enrich the safety assessment procedure as described by the Italian regulation, the ministerial decree, by setting up an as-is model of the building. The digital model is intended as a collector of structural information that can be available for different users and for different purposes, and can be implemented over the time. So the main steps covered are from data collection, data modeling, the structural survey, and the management of the output. The object is to set a BIM-based technology system. So, at the beginning, we start from data collection, from the as-built documentation coming from the archive, or from in this case, the public office of the municipality. And fundamental is the architectural survey. All this information can put together in an effective way by creating a three-dimensional model, parametric three-dimensional model of the building. As you can see, the focus is on structure, but the first approach of modeling is from the architectural part, because it's the one that can be checked, that can be verified with the highest accuracy in the field. The information are translated into objects that are characterized with information that can be related to the geometry, the physical geometry, but also to the analytical one. And it's possible to implement informative attribute about all of these elements, and also it's possible to link external sources and external documents. So, for example, all the presentation that I saw before that can be implemented to an external link in this kind of modeling, in order to provide a comprehensive representation of the structural model. Oh, okay. So, starting from the architectural model, it's possible to create a preliminary structural model of the building. Of course, parametric model require more effort in terms of work, but the creation is a repository of information. And the main aspect is that it's integrated with the other discipline. So coming from the architectural model, it's possible to establish a coherent, a consistent structural model according to the actual state of the building. The building can be visualized in its physical way, but also to the analytical one, and the properties can be related to both of these representations. The analytical representation is automatically returned by the software, and the last model is the calculation model created from the building information model. In order to guarantee an effective calculation model for finite element software, it's necessary to carefully manage the node connection, and for example, within this study, we started to create some guideline in order to maximize the interoperability process between the modeling software to the finite element software. In this case, we started with Autodesk Revit software, and the simulation was done with Advanced Design, FileWriter, and Midasgen. Then the BIM environment was exploited in order to design the structural survey, and the model, for structural design, is necessary to verify materials and with scalerometric and parametric test. And in this framework, the model is used to set an optimal survey plane, map the parametric and the scalerometric test, and gather the data collected during the survey. The initial overlap from the architectural model and the structural models allow to precisely identify the elements and the individual phases of the elements that can be investigated. So, for example, if they are not covered with finishing elements or, for example, furniture. The BIM model is a parametric model, so for example, by introducing a parameter, it's possible to identify these elements also with a graphical representation, as you can see by the central images. Parametric and scalerometric tests are mapped by introducing into the model fictitious objects. These fictitious objects are created from a surface-based family, and the width and the height and the length of the family, that is a cube, are used to manage the dimension of the area of investigation, while the height is the elevation from the ground of the test. In this way, it's possible to design and plan before in a very realistic way the survey, optimizing the time and allowing to reduce the waste of time on the field. Tests are each element of a BIM model is automatically translated into a row of the database. So one test is one line of this database, and it is possible to implement all the information correlated to the test into the model. So the idea is to implement all the data that are necessary for the survey, but can be useful in the future. Here you can see an example of parametric test. The same approach was done for the sclerometric test. So the idea to introduce this fictitious object into the model is to give an evidence of the time and the position of the test. So tests are mapped in terms of number, position, and main characteristics, and the possibility to collect in a structured way the data. It's very important to correlate the family that I told you before is a surface-based family, so it's possible to perfectly place this family on the element that needs to be investigated, and this correlate. It's important to fix this correlation in order to have a complete database. This correlation is not automatically returned by the software. So, for example, we use Dynamo, that is a computational design platform, in order to re-establish and to manipulate data in order to extend the possibility of data. Another added value of this research is to map the overall knowledge of the building. So as you can see, all the elements has parameters that allow to establish the level of knowledge of the element. So this information can be useful in order to assess the building, but also in the future for other users. For example, there are elements that can are perfectly known in terms of because was possible to done the survey, because there's been documentation is present, and so on. To the opposite, there are elements that are totally unknown, and there are intermediate situations. But it's important that it's clear which is the level of knowledge of these elements. The BIM model can also be used as a tool for data check. For example, you can see a comparison between the quantity of reinforcement provided by the project and detected in the field. The cell in red show situation where the cover, the concrete cover is less, or detected in the field is less compared to the project. This is just an example of what is possible to do with this kind of application. Of course, when reinforcement are understand, it's possible to introduce these elements into the software and automatically have drawings or schedules of this element. It's better to introduce this element in a typological way, because they can slow down the operating of the model. So in conclusion, this is just an example of what is possible to do by this methodology and these tools that can support the engineer to govern the process and to adopt increasingly efficient solution because he knows exactly the situation. And this example of structural survey activities is performing a new integrated method, becoming part of the digital process. Thank you.